So now let me go to the, oh, I can go to share screen right there. So now let me share the screen with you guys. Okay, it's right there. Okay. Can you guys see the PowerPoint? No, you can't, right? Okay, right there. How about now? Can you guys see the PowerPoint now? Okay. So let's do this chemistry part now. So chemicals, what are chemicals? It's stuff basically that makes up everything, not our body. I put right here are stuff that make up our bodies, but that's not necessarily true. This bottle right here, it's made up of chemical. The phone right here, it's made up of different chemicals. Water inside the bottle, it's actually made up of chemicals too, right? Now, all these chemicals make up everything that makes up life or no life, the living things or the non-living things. Now, to understand life, we have to do a little bit of chemistry because, as I mentioned, life is made up of chemicals. Now, living organisms are composed, or we call it matter. Matter, by definition, is anything that takes or occupies space and has mass. Feathers, it's a matter. A pencil, it's matter. A computer, it's a matter. Now, this matter, it's made up or it's composed of atoms which make up the elements. Atoms, and then we have elements. So element, by definition, it's something that cannot be broken down into anything else but itself. If I give you silver, you cannot make anything else but silver. Now, probably all of you have seen before a periodic table, right? Now, in periodic table, you have these things there, and in the periodic table, you have, or you place the elements. You place all these elements in there, okay? Now, life requires 25 essential. Essential means what? If you don't have them, you cannot survive, or life cannot exist. Some of them are needed in large amounts. Some of them are needed in very small amounts, or we call it trace amounts. Any of you have any idea which ones are the large amounts? Which one do we need in large amounts? What elements we need in large amounts? The most abundant one that we need, it's actually oxygen. Why oxygen? Because all humans or all animals are made up of water. Now, when you look at water, water is made up of what? Oxygen and hydrogen. Now, oxygen has a larger mass than hydrogen. Atomic mass of oxygen, it's 16 if you look at the periodic table. Let me see if I think I have a periodic, oops, right there. But I don't have the mass of it. But for oxygen, it's 16, the atomic mass. For hydrogen, the atomic mass, it's 1. So based on this, oxygen, it's going to be 16. Hydrogen for water will be 2 times 1. So that would be 2. So that's why there is a lot of oxygen. Humans are made up between 60 to 70% oxygen. A human, it's made up of 60 to 70% oxygen. When you're born, you're fluffy. Like look at a baby, he's very fluffy. And then look at your grandma. Is she fluffy, or your grandpa? They're not fluffy anymore. They're just kind of like drying up. Why is that? Because they lose some of the water, okay? Now here you guys have the elements found in the human body, or the essential to the human body. And oxygen is about 65, as I mentioned, between 60 and 70. Next one, it's carbon. Carbon is very important. Why? Because the carbon is the backbone of all organic molecules. Organic molecules. If a compound or a substance or a chemical contains carbon, it's considered organic chemical, organic substance. Now, what is made up of carbon? Actually, you have DNA, proteins, fats. Fats have a lot of carbon. Now, and also, what is the last one? Carbohydrates, carbs. Carbs also is made up of carbon, okay? Then the next one, it's hydrogen, the essential one. Now, since hydrogen has such a small atomic mass, as you see right here, that's why overall percent it's so much lower, even though it's twice the amount, twice the atoms or the element as oxygen. So there is 2 hydrogen to 1 oxygen. Actually, because of the mass, there is less percent. Then you have nitrogen. Nitrogen is also very, very important, especially in our diet too. Where do we get nitrogen from? Usually we get nitrogen from proteins. Proteins contain a lot of nitrogen. And that's where we get all our nitrogen. Calcium, 1.5%. Now calcium makes up what? Bones. Where do you get calcium from? Lauren, where do you get calcium from? Do you know? Have any idea? Can't hear you.
From dairy.
From dairy products. Yeah, there you go. From milk. That's where you get your calcium. Then you have phosphorus. Then you have some potassium. As you notice right here, they get smaller and smaller. Now these elements right here that are needed are needed in large amounts, and they are called macro elements. So these ones right here, they are called macro elements. The bottom ones right here that you need in very, very tiny, these are called micro elements. This is less than 0.01% basically in the body. And you can read them, you can read which ones they are. And that's why when you go to Costco to buy all those minerals or all those vitamins, you go and you buy because body needs them here. Now there is 2 of them that are important that I want you to remember. Iron, and not fluorine, sorry. Where is it right there? Oh, where's iodine? Sorry, right there. I keep looking for iodine. Iodine and iron, okay? Now, why do I want you to remember these ones? Because iron, it's needed in the blood, in the red blood cells, basically to carry oxygen. If you don't have iron, then basically you become anemic because your body will not produce red blood cells. If you take iron, basically you recover. Iodine, it's another one that we're gonna touch up later. Iodine, it's basically needed in the diet for the actual thyroid. Thyroid, which is in your neck right there. Thyroid is in your neck. So you need iodine for thyroid. If you don't get iodine in your diet, then it's a problem and you end up with diseases, inflammation of the thyroid. Okay? Now, where do you get the iodine from? From your diet. Any of you have any idea? Where do they find iodine? In salt. If you go and you buy salt, you see that it says iodized salt. Iodine it's a vital element for life, okay? Also, you need these other ones. These ones, I'm not trying to say they're not important, but these are the easiest one to remember, okay? Iron, oxygen transport, iodine, thyroid hormones. Now, as I mentioned earlier, some of these trace elements are added to foods. Calcium is added to milk, which is a microelement though, but iodine is added to salt. So far, we talked about chemicals, and then we talked about elements which make up the matter, right? Chemicals make up the matter, and an element is that small one substance, call it substance if you want, but they cannot be broken down to anything else. Now we have to learn compound, which is its cousin of the element. It's the larger cousin of the element. Now, why is considered the larger cousin? Because a compound, it's made up of two or more elements. Two or more elements. Is that clear? Now, basically here, since it's made up of two or more elements, an example would be, let me see, I thought I had it here, oxygen. Oxygen, when it's written like this, oxygen 2. This one, basically, it's also a compound because it has more than one element. It has two, even though it's the same element, oxygen, but it has two or more. So this is a compound, okay? Here you see also water. Water, it's also a compound. Why? Because it's made up of three elements right there, right? Two hydrogen and one oxygen. Is that clear? Another element, another compound, sodium chloride, made up of two different elements. Let's see, sulfuric acid, H2SO4. Is this an element or is a compound? Obviously, it's a compound because it's made up of 7 elements. Is that clear? Here, you could see how they look like too. So look how sodium chloride looks here, the salt that you eat, and it comes from the chlorine, which is toxic, basically is the one they blow it into your pool so they can sterilize the water. And then you have sodium. Sodium is a metal that's found in earth. So this sodium right here, if you combine with this toxic, so you get a very flammable element with a highly toxic element, chlorine in this case right here, and you end up with this good food that you eat. Why? Because when you combine these two, you have to put them under tremendous amounts of pressure and temperature to end up here. Now, the matter that I was talking earlier about, it exists in three important states: solid, liquid, and gas. And all of you have seen this one before. Now, solid, it's rigid and it has a definite shape. Ice cubes, for example, right there. Liquid has a definite volume, but no shape. Why is that? Because if I take this water from here and I put them in a different shape container, it looks different. The shape will change. Agree with that? Now, when you look here, what do you see? You see how these molecules here, molecules of water, how trapped they are? Here, look how trapped they are, how close, combined next to each other, not combined, sorry, attached to each other are. Here, they cannot move. That's why it's that solid state here, because of the arrangement of this molecule. When you look at a liquid right there, they are a little bit flexible. They can move. Now, when you go to gas, gas has no shape and no definite volume. How is that possible? I take the air in a room and I can put them in a larger room. I can take the, for example, you use some cologne, you spray cologne on you. Now that cologne, what is it gonna do? In the house, it's gonna be trapped in a small place. If you put the same amount of cologne outside, is it gonna be trapped in the same small place? No, it's just gonna be basically spread everywhere. It's just gonna spread everywhere throughout the atmosphere. So that's why right here you can see these large spaces for gas. So remember, gas has no definite shape and no volume. It can spread everywhere. Now, when you go from solid to liquid, what is the process called? From solid to liquid, it's called melting. Okay? When you go from liquid to gas, it's called evaporation. Okay? Now let's talk a little bit about the atomic structure. As I mentioned earlier, these elements are made up, oops, right here, I mentioned this matter is made out of atoms composed elements. Basically, this is the larger out of all three, then it's this one, and then there's the atoms, which are the smallest, make up the element, basically. Now, these atoms are the one that give weight or mass to all the elements or the compounds. Now, an atom is the smallest unit that makes up matter. It's not really, there is other smallest particle, but that's considered the smallest that make up the matter for right now. Now, atoms have an atomic symbol. Those are the symbols that you see actually in the periodic table. Oxygen, sodium, chlorine, hydrogen, whatever it is on the periodic table, calcium, all those ones are atomic symbols. Now, an atom has subatomic particles. What is a subatomic? It's smaller. And these are the main three subatomic particles. There is positrons, they were discovered other ones, but these are the main ones that you guys want to remember. Protons, neutrons, electrons. Protons are positively charged, neutrons neutral, as the name tells you, and electrons are negative. Now, if you look right here, this is an element, helium. Helium, if you look at the periodic table, I think it's right here. Helium, has atomic mass 2. Now, why does helium has atomic mass 2? Because it has 2 electrons, or it's not because it has it, but by looking at the periodic table and figuring out how much is the atomic mass, we can identify how many protons, neutrons, and electrons it has. Since it's 2, if you look right here, atomic number 2, helium has 2 electrons, 1, 2, and always electrons revolve outside this area in the middle, and this area right there in the middle is called nucleus. Now, this is different than the nucleus in the cell. It's that just a region, which we call nucleus. Now, if you look here, nucleus is made up of what? Protons plus neutrons. Now, this region right here, which is the nucleus, this is the region that actually gives the mass of the atom. So, by looking at this nucleus area right here, you notice what? What is the mass of, or atomic mass of the helium? When you look right there, what will be the atomic mass of helium? Okay, let's say that you don't know. Let's go here, the next one. Now let's do the reverse psychology. Taking this case, in this instance right here, carbon. Carbon has a mass number of 12, or atomic mass, it's called 12 mass number, or atomic mass. The atomic number is the small number right here. Let me get, actually, oops, no. Hold on, let me go to the internet. Oops, and let me go and show you periodic table. Can you guys see the period, whatever I'm doing right now, going to Google? Yeah? No? Periodic table, you can see? Okay, let me, I guess, share with you. All right. You see right there, periodic table now? So now what you do, you go to images, and let's pick up any of these ones right here that have the actual mass. So let me pick up, this one doesn't have mass. Let me see, this one has the mass at the bottom. Oh, it doesn't, and it's too small. Let me get one here. Okay, so right here, if you guys look here on the side, you notice that right here at the bottom, there is a bunch of numbers. Now you notice at the top, there is this number in order. 19, 20, 21, 22, 23, 24, blah, 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 so forth and so on. Now, when you look at this number, at this each element right here, you notice that it has a small one at the top and it has a larger one at the bottom. Okay, now always the smaller number right there, it's the atomic number. The large one is the atomic mass, the atomic mass. Actually it tells you right here too. The symbol, the name, the atomic mass, and the atomic number. Now, let me go here back to my stuff here. And let me go to my slide. And now here, when you guys look, same thing. For carbon, atomic mass 12 is the large number. The mass is the large number. Atomic number is the lower number. Now, what do these numbers represent? These numbers are there for a reason. The mass I mentioned to you earlier, it's given by what? By the nucleus, right? Nucleus. The atomic number right there, the atomic number, it's given to you by the protons or electrons, the number of protons of electrons. Now, what would be the atomic mass when you look at helium here? It's the actual nucleus. How many particles do you see in the nucleus? There is 1, 2, 3, 4. So the atomic mass would be 4. What is the atomic number? What is the atomic number for helium? So you count either the number of protons, 1, 2, either the number of electrons, which is also 2. Okay? So when you look at an element at the periodic table, the large number, it's always the mass. Why? Because it's made up of these protons plus the neutrons. Whatever it's inside the nucleus, protons plus neutrons, okay? Now, atomic number, it's the actual number of protons or electrons. So let me make up an element right here. Let's assume that you have element Mi from Mitch, and it looks something like this. 17 and let me see, and 36. Now, based on this one, can you tell me how many electrons this element has? Lauren, can you try, or Luis, or any of you? Just try it. I want to see if you guys understood. So you have this element Mi that I made up, 17, 36. 17 would be what? The atomic number. 36 would be what? The atomic mass or the mass number. Now, based on these two numbers right here, can you tell me the number of protons, electrons, and neutrons? How many protons will I have?
17.
17. Because I told you right here, this number tells you the protons or the electrons. How many electrons I have then?
17.
17. How many neutrons do I have then?
36 minus 17.
There you go. 36 minus 17, so equal 19 neutrons. So I hope it makes sense for you, Sadie and Laura now. So you just got to practice some of this one. And guys, just practice some of these ones. Just grab a periodic table and just practice some, because you're going to do good in the exam. Otherwise, you will struggle and you will not have time if you don't practice. All right, now there's a little variation. Sometimes you're not going to see this one in the periodic table, but sometimes some elements have isotopes. Isotopes. What is an isotope? Isotope is basically an element that has the same number of protons and electrons, but the number of neutrons changes. It changes dramatically. Now, the problem with this isotope, and you're not going to find them too much in nature, they are in very, very small amounts. They are very, very unstable. Unstable, which means what? They start decaying or disintegrating. So while they disintegrate, the problem is they emit radiation. Radiation, it's a form of energy. This energy it's really bad for organisms because it's very, very small packets and it's very bad. You guys heard about radioactive elements. You don't want to be next to plutonium or uranium or some radioactive element or chemical because it's going to kill you. It's going to actually break down everything inside you. So you don't want to be next to it. So that's the problem with these isotopes or these radioactive isotopes. Now let's see here. We have carbon. Carbon has 2 extra carbons or 2 extra isotopes. Carbon 12 is the one that we just saw earlier, 6 and 12. Carbon 13, it's also 6 and 13. Carbon 14 would be 6 and 14. Now remember, that 6 right there is the atomic number. Now the atomic number gives me the number of protons and the electrons. So if you look right here, they have the same, all 3 isotopes, they have the same number of electrons and protons. That one will never change. The only change between these 3 isotopes is what? It's the number of neutrons. Now, the number of neutrons differs. Why? Because the atomic mass changed right here, if you notice. 12 minus 6 means 6. 13 minus 6 means 7. And 14 minus 6 means 8. So the number of neutrons changing. These are basically the isotopes. Isotopes. Any questions? No? Okay. So as I mentioned earlier, the problem is this isotope, they decay or they disintegrate because they are very unstable. And they emit energy, which is a form of, they emit radiation, sorry, which is a form of energy. Now these isotopes are actually, some of them are used to treat cancer. You guys heard about that, right? The radiation. Now, radiation can be detected with this instrument. It's called Geiger counter. It's just one of those, the beep, 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 beep you saw in Transformers when they, at the beginning, when they're arresting the, where they try to arrest the 2 of them in the car right there. Now, the problem with these isotopes, there's the accidents. They can lead to release of this isotope in the atmosphere. Now, nuclear power plants use isotopes to produce energy, to produce heat, which will turn into energy or electrical energy. Now, there is 2 main disasters, 3 right now, with the Japan one, the Fukushima one, right? I think it was Fukushima. I don't know if I spell it right, but you guys can figure it out. Chernobyl, 1985, was in Ukraine, where that basically nuclear power plant released a lot of radiation in a very short amount of time in the atmosphere, and it started basically polluting the whole Europe over the next couple of days. Now, remember, these isotopes have one problem, one major problem, which is what? They can lead to loss of life or they can actually kill you. That's the problem. So you don't want to release them in the atmosphere or you don't want to be next to them. The second one, disaster, was in 1979 at 3 Mile Island, which is our nuclear power plant in Pennsylvania. So here, basically what happened, here was in Chernobyl was a complete meltdown of one of the units, complete meltdown. What does complete meltdown means? It was not that somebody got pissed off and they had a complete meltdown, but it's basically, there was a reactor with a lot of this isotope loaded in there, and then it overheat and it melted the whole core of it, and then the whole radiation, all this radiation was emitted into the atmosphere and the winds carried everywhere. 3 Mile Island, it's pretty cool. Actually, for 3 Mile Island, they have an enclosure. I don't know if you guys drove to San Diego, any of you, but if you drive to San Diego, at one point, there is 2 of these things that stick out like that. And I know you students, and I know I learned from other people because, you know, I didn't grow up here. They call them the boobs whenever you drive down there. Now, those are actually the reactors for our power plant that they have in San Onofre right there. Now, that power plant is going to be shut down because I guess they had cracks on it. And a lot of this radiation still escapes or hasn't escaped any from San Onofre. But if there is cracks on these domes right here, they cover basically where the reactor is in here, because the reactor is right in there. If there is a crack, and these walls, these domes are very thick. They're about a yard thick. Imagine like this thick. So this wall is super thick right here. And if there is cracks in it, this radiation is so tiny that can escape. And you guys know that radiation is very tiny because you went to get an X-ray, right? X-ray uses radiation. Now, when you go there, what do? Do they just bombard you with a lot of radiation? That guy just, or that person, the radiologist, or what he does, poof, clicks and releases a little bit of radiation, which passes through you and comes out. And behind you, what is it always? There is a film, and that film records the shape or whatever it's inside you. That's why when you go, they look at the lungs, bones. If you have broken bones, they take X-rays. So anyway, back to this stuff right here. Luckily, the 3 Mile Island was built properly, and it had this cover to trap all this radiation that was emitted from there. Now in Chernobyl, this one had no cover. It just had only the actual, core right there. So the whole radiation escaped out. Fukushima also had, but Fukushima, there was an earthquake problem, and problem cracked the covers. And then also they had those storage tanks where they were storing the water. And that's another one that end up in the ocean. So that's the main problem. You guys don't need to know all this technical stuff, but I'm just trying to make it interesting. So I don't want to keep teaching. If we are face-to-face, it's much easier, trust me. I can actually even show you stuff there too. All right, periodic table. And I think that's the last one that I'm gonna do for today. And then I'm gonna pick it up on Wednesday, but periodic table. It's that basically a table where the elements are organized or stored, I call them, stored, quote, stored. Here, you have the periodic table where you have all the elements organized or stored in it. Now, a periodic table it's broken down into groups and periods. It's organized into groups and periods. Now, periods go like this across. Groups, if you notice at the top, go like this down, okay? Now, periods is not really that important because they are just organized based on their number to be in a sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah, 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 okay? But groups, when they place these elements, that's why they build this periodic table. What that guy that came up with this periodic table noticed that these elements in the same group right here have similar chemical and physical property. What is a property? Do you guys know? A physical property? What is a chemical property? Physical, it means that they kind of look the same. Physical appearance. It's like you go out and you look how a girl or a guy looks like. That's physical appearance. Chemical property, basically, it's you have to know what's happening inside that person, but you don't get to see that unless you really experiment with that person, or you get to know that person, or you get to know the elements. So when you look right here in, for example, in group 3, boron, aluminum, germanium, indium, and tellurium right there, they have basically, they have the same, or not, I'm sorry, not the same, close chemical properties. They have relationships, basically. They are related to each other. This would be the cousins, basically, in the same group. Is that clear? Yes or no? So periods, you go across. Groups, you go down, okay? Elements in groups have similar chemical and physical properties or characteristics. I have them here, period, and you have the column right there. Any questions? Any questions? No? Okay. So I guess that's all for today. And I'm going to finish it up, this one, next Wednesday. Any questions?